Hello, it's Valentine from Simplistic, and we're going to take a look at a problem of which basically asks us how to calculate the pH of a buffer solution using two methods. The first method is we'll use the Henderson Hasselbalch approach, and then the second we'll use the equilibrium approach. Okay, so let's take a look at this. The concentration of the acid that is given to us. Let's write that out here. Concentration of the acid is 0.250 molar. And the concentration of the base is this compound devoid of the K, so Cn minus, that's what the base is. So that's equal to 0.170 molar. Okay, and just for clarity, HCN is the acid and Cn minus is the base. Okay, so we have the two concentrations. The problem also gives us what the pK is, 9.31, so we don't have to do that math. So let's just go ahead and plug this into the Henderson-Hasselbalch equation. So we write pH is equal to pKa plus log concentration of base over concentration of acid. So pKa is 9.31 plus log concentration of base is 0.170. Concentration of acid is 0.250. Upon simplifying this side, we end up getting 0.17 minus 0.17. And then the left side is still the same. And we crunch that. Well, I'll just go ahead and write it out here to save some space. It's 9.14. That is the pH of the buffer solution. Now let's see how we can calculate this using the equilibrium approach. So for the equilibrium approach, we need to take this acid and we need to write the acid ionization equilibria for it. So if we write that out, we'll get HCN aqueous plus H2O liquid. And that gives us H3O plus aqueous plus Cn minus aqueous. All right, so let's create an ice table, initial change in equilibrium. So initially, what we have is 0.250 molar of the acid. We have nothing of H3O plus, but we have some Cn minus, which is 0.170 molar. There you go. And then the change is going to be minus X out here, plus X out here, plus X out here. And then at equilibrium, we have 0.250 minus X. We have X out here. We have 0.170 plus X. All right, now Ka for this is given as H3O plus times Cn minus over HCN. H3O plus is X times 0.170 plus X over 0.250 minus X. At this point in time, we can assume that X is really, really small. So we can go ahead and pretend it's not there. So that gives us X times 0.170 over 0.250. All right, so if we simplify that, we get X times 0.68. Okay, and then if we solve for X, we know that Ka is given to us as 4.9 times 10 to the negative 10. So that equation becomes 4.9 times 10 to the negative 10 is equal to X times 0.68. So if we divide both sides by 0.68, we get X is equal to 7.21 times 10 to the negative 10. All right, at this point in time, if we take since X is the H3O plus ion concentration out here, so if we take the negative log of X, we get the pH, right? So that is negative log of 7.21 times 10 to the negative 10, which ends up being 9.14. Now, that is our final pH. So as you can see, if both the methods, if we did everything correct, then the pH from both the methods should be the same quantity. The one last thing you want to do is you want to check if X out here, because we made an assumption that X is really, really small, we want to check if our assumption is correct. So to check that, we want to take the value of X that we got, which is this, and we want to divide it by the quantity it was subtracted from or added from. And as you can see, if we get 0.05, so if we get 5% or less, then the assumption is correct. Now, because this number is such a tiny number, just look at the power of 10. It is such a small number compared to this one or this one. Therefore, we can safely say that our assumption is correct. Now, how would you make that decision? Well, take a look at the power of 10 out here and out here. If you express this number or this number in scientific notation, it will be 1.70 or 2.5 times 10 to the negative 1. So I'll just write that out in green out here. 1.7 or 2.5 times 10 to the negative 1. So if you take something that's 10 to the negative 1 and you compare it with something that's this, that's like a billion times smaller. Okay, so that's like way smaller. So 0.05, the assumption that we made is absolutely correct, because this is just way smaller than this. Sorry, this is just way smaller than this or this. Okay, all right, so that's where the problem ends up. I hope that made sense. Thank you for watching.